Have you ever stopped to actually think about how much of the internet feels, well, kind of like magic? I mean, we use massive global applications every single day, and they're usually so seamless we just treat them like a natural resource. But behind that smooth, error-free facade is an absolute storm of hidden chaos. So, in this explainer, we're going to pull back the curtain on distributed systems. We're looking at the messy, physical reality of data-intensive applications and exploring exactly how engineers build highly reliable systems out of parts that are, frankly, inherently unreliable. Let's get into it.
To really understand this, let's just start with a scenario. Imagine you're using a popular restaurant booking app. You find the perfect table for Friday night, and you tap that reserve button. But in the exact millisecond your request is traveling through the system, disaster strikes. Behind the scenes, a physical server abruptly dies, and network call times out. A database replica suddenly slows to an absolute crawl. It is total chaos in the data center. Yet a second later, a green checkmark pops up on your screen and you get a success confirmation. So, how is that even possible? How did the system survive all of that without you ever noticing?
Well, the answer is reliability. And the absolute most crucial point here is that in distributed systems, failures are completely normal. Reliability doesn't mean building a system where nothing ever breaks, because that is physically impossible. True reliability means intentionally designing architectures that keep working correctly. They perform their expected function, they keep your data safe, they handle the expected load, and they even survive unexpected user input, even when internal things go drastically wrong. It's essentially the art of hiding the chaos from the end user.
Here's a roadmap for today. We'll start with faults versus failures, then look at hardware faults, software errors, and human errors. After that, we'll see fault tolerance in action and finally wrap up with the reliability trade-off.
Okay, Section 1. Faults versus failures. What's the actual difference?
So there's a really clear boundary between these two concepts, and engineers mix them up all the time. A fault is when one specific component misbehaves. Maybe a hard drive gets corrupted or a single network switch just randomly reboots. A failure, on the other hand, is when the entire system stops meeting its promise to you, the user, like when a restaurant app crashes and you just can't book your table. Now, because you literally cannot eliminate faults, the ultimate goal of a reliable system is to prevent those individual faults from cascading into total failures. In fact, some companies actually deliberately trigger internal faults, like randomly killing their own servers in production, just to continually test and prove that their systems won't fail. Crazy, right? But it works.
And that's why reliability is a foundational pillar of any data-intensive application. It sits proudly right up there alongside scalability and maintainability. Because think about it. Without reliability, a system that scales infinitely is really just a system that fails at a massive scale.
Moving on to Section 2, hardware faults. Let's talk about the messy physical reality.
We all know that physical machinery breaks down. Hard disks crash, power gets cut, RAM modules corrupt data, and yep, sometimes someone just accidentally unplugs the wrong cable. Now, if you only have a single computer, a hardware fault usually means a total system crash. But in a massive data center cluster running tens of thousands of disks, hardware death isn't some rare anomaly. Statistically, it's literally a daily routine. And to make things even more interesting, in modern cloud environments, virtual machines are often designed to prioritize flexibility over single machine reliability. This means they can just vanish without any warning whatsoever. So how on earth do we survive this daily hardware death? Well, the classic solution is redundancy. We arrange things so that when step 1 happens, a component fails, step 2 immediately kicks in, routing the work to a redundant backup. This means setting up disk arrays where data is perfectly mirrored, utilizing dual power supplies, and replicating your data across entirely different physical machines. If one node dies, another one simply takes over. This allows the service to just continue on uninterrupted, while an engineer quietly replaces the broken hardware in the background.
All right, Section 3, software errors. Let's look at systematic bugs.
While hardware faults are usually random and isolated, like one broken disk doesn't mean the disk next to it is going to break, software bugs are systematic. They correlate across nodes. A dormant bug in your software might be totally fine for months, until a specific, super rare set of circumstances triggers it. And when that happens, because the exact same software is running on every single machine in your cluster, they might all crash simultaneously. A famous example of this was a leap-second bug in the Linux kernel that caused countless applications globally to hang at the exact same moment. Other examples include memory leaks, a bad deployment, rare input bugs, retry storms, configuration mistakes, or cascading failures, where just one small slowdown overloads the rest of the entire system.
Now, there is no magic bullet to entirely prevent software faults, but we can definitely build architectures to mitigate them. We do this by thoroughly testing our assumptions, carefully isolating processes so one single crash doesn't take down the whole server, allowing applications to quickly restart, and heavily relying on continuous production monitoring. The system needs to be constantly measuring its own behavior and automatically raise an alert the second something looks suspiciously out of bounds.
Which brings us to Section 4. Human errors are well-intentioned but unreliable operators.
So, despite all our focus on servers and code, studies consistently show that human configuration errors are actually the leading cause of outages in large internet services. They vastly outnumber pure hardware faults. Even with the absolute best intentions, humans are simply unreliable. We make mistakes.
And because we can't stop humans from making mistakes, we have to design operational guardrails that prevent those mistakes from causing total system failures. This means providing non-production sandbox environments where engineers can experiment safely with real data. It means robust automated testing, strict access controls, and detailed runbooks. But crucially, it means designing systems that allow for incredibly fast code rollbacks. That way, if a bad update does go out, it can do reverse before most users even notice something is wrong. Add detailed telemetry to that, and you basically give humans the tools to spot their errors before they become catastrophic.
Section 5. Fault tolerance in action. Let's put it all together.
Let's go back to our restaurant app. You hit reserve. The app server starts processing your request, but right before it finishes, a hardware fault causes it to spontaneously shut down. That's a failure, right? Actually, not quite. The load balancer sitting in front of the servers detects the timeout and immediately reroutes your request to a healthy, redundant app server. Meanwhile, the database writing your reservation notices a replica is running slow due to a network glitch, so it swiftly reads from a different replica instead. Finally, the worker responsible for sending your confirmation email has a software memory leak and crashes, but guess what? Your email isn't lost. A message queue safely holds that notification on disk until an automated restart spins up a fresh worker to grab it and send it straight to your inbox. You, the user, saw absolutely none of this, you just got your table.
Finally, Section 6, the reliability trade-off, cost versus engineering effort. Here is the catch. As you increase a system's reliability guarantees, the financial cost and the engineering complexity scale up linearly, sometimes even exponentially. Think about a banking system handling global transactions. It requires an extremely high level of reliability because a failure could mean catastrophic financial loss, not to mention legal trouble. So they absolutely must pay for massive redundancy and intensive engineering. But a small hobby app, it might only need moderate reliability. If you over-engineer that hobby app for a scale and perfection you just don't need, you're really just wasting money and slowing down your ability to launch new features. You always have to choose the right tool and the right level of resilience for the job.
So what should you really take away from this explainer? Well, the core lesson is that distributed systems survive by literally embracing failure. Reliability means expecting faults at absolutely every level: hardware, software, and human. It means preventing those isolated faults from becoming total user-facing failures by utilizing smart redundancy, isolation, strict guardrails, and rapid automated recovery. It is an ongoing, highly active process of constantly monitoring and reacting.
And doing all of that ensures your system stays upright, even when things are going completely wrong under the hood. But what happens to our resilient restaurant app when it suddenly goes viral and traffic spikes 10,000%? Well, next time, we're diving into scalability and performance and exploring exactly how systems behave as load grows. See you then.